Welcome back. As always, I'm Mr. Gass. Today what we're going to be exploring is three different scenarios in which two lines intersect each other and intersect a part of the circle. In the second part, we're going to prove the relationship in two of these cases, but not the third. So let's start by doing a little exploration of this situation. So the first one we're going to look at is intersecting secants or chords. We can say that these are intersecting chords because their intersection point occurs inside the circle. So really what I'm looking at is chord AB and chord CD that are intersecting inside the circle. But of course, AB, the line AB is a secant and line CD is also a secant. But because the intersection point happens inside a circle, we say that we're just looking at the intersecting chords part. Now, no matter where these segments are, you might notice down here at the bottom, I'm calculating the lengths of AP, that segment, the length of BP, that segment. I'm calculating the length of CD, and I'm calculating the length of DP. And at the bottom, I'm doing something curious. I'm multiplying AP times BP, and I'm multiplying CP times DP. And this is curious. Their products are exactly the same, regardless of where these two segments are. That's really interesting. So somehow when the two chords intersect, the segments that they are broken into, the product of those segments, AP times BP and CP times DP, that those two products are equal. Now, if the two chords intersected outside the circle, now we're really talking about two secants, because AB, that chord, and CD, this chord, they don't intersect inside the circle. Now we're looking at two secants intersecting at point P, but the same relationship still holds, that AP times BP, those two secant segments, AP times BP, and CP times DP, that those two segments are also, the product of those segments are also always equal. So regardless of where these two secants intersect, whether they intersect inside the circle in the situation of a chord, or outside the circle in the situation of two true secants, the theorem still holds that AP times BP equals CP times DP. So that's the first situation we're going to look at. The second situation then you might ask yourself is, well, what happens if we have two tangents? So if we have two tangents that intersect, they're naturally going to intersect outside the circle. And again, regardless of where that intersection occurs, look at what happens. That length of that tangent segment, AP and BP, those two lengths, regardless of where A and B are, the length of each one of those tangent segments appear to be always equal. And so that's going to be our theorem, is that intersecting tangent segments have equal lengths. When we go to do this proof, we're going to draw in some extra lines. We're actually going to do that in both proofs. But I just wanted to give you a little visual of what we're going to do so that you can preview it. We're going to draw in those radii, and then we're going to draw in the segment from the center to that point of intersection. And we're going to examine these two triangles. You might want to pause the video right now to see if you can prove to yourself why AP and BP are always congruent. The last way that we can have two lines that intersect each other with regards to a circle, we've had two secants intersect, we've had two tangents intersect, but what if we had a mixture? What if we had one tangent and one secant? The proof of this is a little bit harder, and the relationship is a little stranger, because it's a little bit, what I'm capturing here in the blue is the length of the tangent segment, PC, and I'm still capturing PA and PB, those secant segments. And what we want to capture is PC times PC. You can kind of think that the bottom one here, PA times PB, that's exactly what we were expecting. The two secant segments multiplied times each other. But here with PC, we don't have two different secant segments because we only have one point of intersection with the circle. So we're just going to multiply PC times itself. And now we've got that equal relationship. So we've got our theorem, or at least our conjecture, is PC squared equals PA times PB. The proof of this one is fairly difficult, and we will possibly talk about this later on when we get to section 25. So let's pause this for now and do a quick little transition to the DocCam. So here we are, and we're ready to investigate the proofs of at least two of these theorems. So the first thing we're going to do is we're going to do the proof that intersecting chords get broken into two segments, AP and BP. And when we multiply that, that will be equal to the product of CP times DP. So that's the first proof that we're going to do. And this proof is going to rely on a fact that we're actually not going to prove until next section. So for now, we're just going to accept it as a fact, but at the end of the next section, we'll actually understand why the proof of it works. So the first thing we're going to do is we're going to start by drawing some extra segments in here, and we're going to draw in segment AC. We'll draw in segment AC. And we'll draw in segment BD. So we've drawn in those two extra segments there. And now what we're going to do is we're going to look at these two triangles, the triangle here on the left and the triangle on the right. So what do we usually do? Well, we usually look for some congruencies. In this case, we're going to look for some congruent angles. And one that might jump out to you right away is some vertical angles. That these two angles at P, they're going to be congruent because of vertical angles. And the second set of angles that we're going to find that are congruent, this is the fact that I'm going to ask you to just take on faith right now. And in a moment, in the next video, we're actually going to prove why this is the case. But for now, we're just going to have to accept it. And what we're going to accept here is that angle A that's down here and angle D, they end at the same place on the circle. They both end at CB on the circle. And we're going to take this as a fact now, but we're going to prove it later. If two angles have a vertex on the circle, angle A and angle D have their vertices on the circle, and they both end at the same place on the circle, in this case B and C, then that means that these two angles are going to be congruent. And from that information right there, we know that that means we have angle-angle similarity. So let's write our similarity statement. Our similarity statement is going to be that triangle CPA, that's going to be similar to triangle BPD, and that's by angle-angle similarity. That's by angle-angle similarity. And so now we can write, we can write a proportion. So the proportion that we're going to write is AP. AP corresponds to DP. And then we're going to write that CP, that corresponds to BP. And then we can cross multiply. And when we cross multiply, When we cross multiply, what we're going to get is AP times BP equals CP times DP, which is exactly what we wanted to prove. And we proved this for two intersecting chords, in this case, two secants that intersect inside the circle. And the proof is very, very similar if we have two intersecting secants, those two that intersect outside the circle. And you're going to have to find your own triangles for those and see if you can set up your own similarity statements. I would suggest waiting until after the next section to do that proof so that you can understand more clearly why angles A and D are congruent. Okay, now let's do the next theorem. The next theorem says that if we have intersecting tangents, that those intersecting tangents are also going to have the same length. So let's start by drawing our two tangents, and remember that a tangent is a segment that just, or is a line that just intersects a circle at one point. So we're going to do our best to make this intersect at just one point. There we go. There's our point P. This will be our point A right there. And we'll do another one over here. And this will be our point B right there. Now, as I was showing you in the Desmos demonstration, what we're going to use here is we're going to draw in some radii. And radii are very useful for two reasons. One, for one circle, they are always the same length, so that helps us to create some congruent line segments right away. And two, when we have tangents, we get to create right angles. Remember, that was the fact that we learned in the last video. So we're going to draw in a radius here, and we're going to draw in another radius here. We have our two radii, and they are the same length because they're both radii. And then what we're going to do is we're going to finish this off by making a triangle. And we're going to make that triangle, we're actually going to make two triangles, by drawing in segment OP. So we're going to do that. And we have two triangles here. We have the triangle on the top, triangle happy face, triangle star on the bottom, and this segment that is drawn here in green, that's going to be congruent to itself. That's the reflexive property. And remember when we drew in the radii that they're going to be perpendicular to the tangents at the point of tangency. So what we have here is, well, let's put 3 little marks there. What we have here is we're going to have two triangles, two right triangles that have a common leg and a common, or congruent legs and a common and congruent hypotenuse. So let's write this out. What we have here is we've got triangle AOP is going to be congruent to triangle BOP, and that's going to be by HL, hypotenuse leg theorem. Hypotenuses are congruent for both of them. Legs are congruent for both of them. So we have hypotenuse leg, and that means that the remaining corresponding parts are congruent by CPCTC. And that's what we wanted to show. We are all done here with our proof. We've shown that these two tangent segments, AP and BP, are congruent. That means that AOBP is what kind of shape? Think about what kind of shape that is that we've made there just by using some radii and two tangents. All right, next time we're going to talk about exactly why our theorem here for intersecting chords worked, why these two angles A and D were congruent to one another, and we are going to talk about angles in circles. So that's for next time, and I will see you then. Take care.